Log on, tune in, find out. Another good idea from Cambridge.
This afternoon session, I'm pleased to introduce the first speaker, Achar from Louisiana State University. We'll talk about staggered sheaves.
Okay, thank you very much. I'd like to thank the organizers for inviting me to speak here. So I'm going to talk about, these things called staggered sheaves, which are meant to be some attempt to duplicate some of the properties of perverse sheaves in the coherent setting. And they seem to have a lot of extra nice properties, which are analogs of the properties that are useful when you're doing things with perverse sheaves in representation theory. So the results I'm going to talk about come from these 5 papers. And if you try to look at these, I should warn you that in the later ones, sometimes we realize that the notational choices made in the earlier ones was not necessarily the best one. But there's a survey paper which sort of covers the things I'm going to talk about today. And it's at least consistent with itself. Okay, so I'm going to start off with some really elementary things. I'm trying to imitate something about perverse sheaves, so I want to spend a little bit of time going over some features of perverse sheaves which are no doubt known to most people here, but I just want to draw attention to them. So the setup is going to be this. So X is a variety with a fixed stratification. So let's call that script S. So script S is the set of strata, and for a stratum, which I'll denote by ordinary S, I'm going to write I sub S for the inclusion map. Of course, everything is going on in the derived category. So dbx stands for the bounded derived category of sheaves on X. And well, we don't actually want the whole bounded derived category. We want to stick to talking about certain kinds of objects. And the kinds of objects that are relevant are these ones. So I'm going to call an object in the bounded derived category, of course, everyone knows this definition, but I want to write it down anyway. So this is a complex of sheaves, and it's said to be constructible if the following condition holds. What I want to do is look at what it does on each stratum. So I'm going to take its pullback to each stratum, and then I get a complex of sheaves on that stratum, and I want to require that all the cohomology sheaves of that complex be locally constant sheaves. Okay, so this is for all strata S and all integers K. Okay, so that's of course a well-known definition. And then the class of objects which have this condition, that's called dbc of X, and that's the full subcategory consisting of such objects. Okay, and then the next little bit of machinery that I need is Verdet duality. So Verdet duality is a functor from the bounded derived category of sheaves to itself, and it's an anti-auto equivalence. it's well, it's the sort of I mean, it's the thing you get in the world of sheaves if you try to generalize the process of taking the dual of a vector space. And so if you do that twice to a finite dimensional vector space, of course you get the same thing back. And well, dual of a vector space, that's the operation of taking Hom into the ground field. And we're going to do the same thing here, except it has to be sheaf Hom, and it's in the derived category, so it's sheaf R Hom. And it's not maps into the ground field, but into the dualizing complex, which I'll denote by omega x. And well, I'll just write down what omega x is, even though I guess I won't really have need of it later on. So omega x is well, it's the Schrick pullback of the constant sheaf from the map from the variety to a point. I wrote C here, but later I'm going to want to talk about L-adic perverse sheaves, so the appropriate constant sheaf, which plays the role of the ground field. Okay. And here's let me make a statement first. So here's an elementary fact about these two things. So I've got a constructible category and I've got Verde duality. And an easy fact about these is that Verde duality preserves the subcategory of constructible complexes. And that lets me write down the following. So perverse sheaves are the objects of a category P of x with the following two properties. So one is that, well, it's an abelian subcategory of the category of constructible objects. So the derived categories themselves are, of course, not abelian categories in general. And it's stable under Verde duality. That's not to say that every single object is. Some objects are stable under Verde duality. Some are not, but the dual of a perverse sheaf is always another perverse sheaf. And these two properties, these are close to being a definition. What I mean is that it's almost, well, here's what would be true. If I told you to take if I told you to look for a maximal abelian subcategory which is stable under Verde duality and added a little technical detail about what happens on a single stratum, then you could prove that there's a unique such subcategory, and this is it. Okay. So there's not a lot of information here about what the structure of this category could possibly be. But then after the fact, so after proving, well, maybe not really after, but around the same time as proving that P of x is uniquely defined by that plus whatever else you need. Then you discover lots of other nice things. So P of x has a lot of good properties, and here are some of the properties that it turns out to have. One is that every object has finite length. There's a uniform description of the simple objects. So there's a way to construct all simple objects, and that's of course the intermediate extension functor, or the IC functor. And there are more properties in this list also, and I'll mention some of the other properties later on in the talk. Okay, so the aim for this talk is to duplicate this as much as we can in the setting of coherent sheaves. The first thing we need is a tiny bit of notation. I'm going to write script dbx, and my convention throughout is going to be that script letters stand for coherent things and Roman letters stand for constructible things. So script dbx is the bounded derived category of coherent sheaves. So let me just start trying to write something down, and let's see what comes out of it. So the two ingredients here were the word constructible and Verde duality. So if I try to write down an analog of constructible, well, what do I want to require? So I want to take a complex of coherent sheaves. I'm going to pull it back to a stratum. There's a slight technical issue already, because if I want to work with coherent sheaves, then I want to take coherent pullback, which is not an exact functor, so I have to take its left derived functor. That's not a big deal. But then I want to look at the cohomology sheaves of that complex. And then, well, what's the analog of locally constant? Well, that should be locally free. I guess you could phrase locally constant as locally free module over the constant sheaf, and this is a locally free module over the structure sheaf. So that's the kind of definition we'd like to write down. And then we need some kind of duality, and there's a well-known, well-developed duality theory for coherent sheaves, and that's Serre-Grothendieck duality. So this, I'm going to use the same letter, this Blackboard bold D, because I don't know how to make a calligraphic version of that. And now that's a functor from script dbx to itself. And again, it's an anti-auto equivalence. And in fact, it's it's also given by Arham into a suitable object. And I'll denote the object we need in the coherent world with capital omega x. So this is the coherent dualizing complex. This is if x is smooth, then this omega x is something quite familiar. It's a shift. Oh, there's a shift in here that I want to keep around, which I'm not going to specify at the moment. But this is a shift of the canonical bundle. Okay. And so so what I want to do, based on what I did on that board, was is just find a duality stable abelian subcategory of, well, not the full bounded derived category, but let me put that in quotation marks, the subcategory where this condition like constructible holds. Okay, this doesn't work. There are lots of problems with it. And the first problem is that this category DBCX defined by this condition is not a triangulated subcategory. This is actually a really elementary assertion. This is just saying that if you have a map of vector bundles, so of locally free sheaves, then the kernel and the co-kernel need not be locally free. So that's no good as a setting for talking about T structures and these kinds of abelian categories and whatnot. So that seems to stymie the plan. But let's ignore that problem and see what other problems we'd have if we overcame that. The second problem is that the sheaf operations, by which I mean the usual things you can do with sheaves, push forward, pull back, that kind of thing, they don't respect, or they don't preserve the well, I won't tell them the variety, because of course usually you're moving to a different variety, but they don't preserve the property of being in the bounded derived category of coherent sheaves. This is not too bad for the pullback functors. So if you take coherent pullback to a stratum, or if you take shriek pullback, for which you also have to take a derived functor, these give you complexes of coherent sheaves, but they're unbounded on one side. So these are not bounded complexes. But the push forwards are much worse. If you take the ordinary push forward along a map, then it takes a coherent sheaf in general to a quasi-coherent sheaf. So this gives complexes of quasi-coherent sheaves. And the shriek push forward is much worse. Well, maybe it's not much worse. It does exactly the dual thing. A quasi-coherent sheaf is an end object in the category of coherent sheaves. So when you take shriek push forward, you get the dual thing. You get pro objects. So you get complexes of pro-coherent sheaves. And of course, the problem is that Serre-Grothendieck duality doesn't work so well in these settings. Taking the dual of an infinite dimensional vector space is not always a reasonable thing to do. There's yet another problem, and this is the problem with requiring self-duality of the category, of the putative category, which we can't even write down a definition of yet. Let me just for a moment consider a really easy variety. Let's just take affine n space. Okay. In the constructible case, the dualizing complex is just the constant sheaf shifted by twice the dimension of x. Okay, and the consequence of that is that if you take the constant sheaf and you shift by the dimension of x, that's self-dual. Let me just write this out. This is actually, I mean, this is kind of a trivial statement, but I'll just write it out to be clear about what I'm saying. The assertion is that, well, R hum of the constant sheaf into itself is itself. And then the way these shifts work with these kinds of derived category calculations is that the shift you get on the outside is going to be this shift minus this shift. So of course you just get that. In the coherent case, well, the canonical bundle of affine n space is trivial. And so you just get the structure sheaf. And I didn't specify the shift over there. The shift, well, there are different ways to normalize this, but with the normalization I want to use, the appropriate shift here is the dimension of x. And so you can see by the exact same calculation that the structure sheaf shifted by half the dimension of x is self-dual. So if this shift is supposed to be an integer, clearly that imposes a restriction on the variety. So that's a problem. Okay. So now let me tell you about some ways to fix the problems. Okay, so the first problem was that the word constructible, I mean, this definition, which is the analog of constructible for coherent sheaves, doesn't work because of this problem. But if you have a variety with extra structure, and you look at only coherent sheaves that respect that structure, sometimes that problem just goes away by magic. And one such instance, which fortunately enough comes up in representation theory, let me write this in first. So with extra structure, this thing which I call dBcx may be okay. And an example of the extra structure which makes it okay is when you have a group action and the orbits give you the stratification. So if you have a group acting on X with finitely many orbits, and the strata are the orbits. So in this situation, what problem 1 says is that, well, if you have a map of locally free sheaves on an orbit, well, on an orbit, an equivariant sheaf is automatically locally free. So the kernel and co-kernel are automatically locally free. So then problem 1 disappears. And this setting, where you have a group action with finitely many orbits, I'm going to impose this as an assumption, and this assumption will be enforced for the rest of the talk. Okay. So what about problem 2? Problem 2 had to do with these sheaf operations. You can get around some of the problems in the following way. You can rewrite the construction of the abelian category of perverse sheaves to use only the pull-back functors. So is star and is shriek. And the fact that these turn out to be bounded, they cause technical difficulties. Like you have to pay attention to what derived category in you're in at a given moment, and sort of take care to truncate things when they need to be truncated, and that kind of stuff. With some care, the construction of the category goes through in the coherent case, and I think this was originally discovered by Deline and written up in a slightly different way by Bezrukhovnikov. But we needed something more. Part of what makes perverse sheaves so great is that you have a concise way to name the simple objects in the category. So you have this IC functor. And the problem with that is that, I mean, in the usual constructible case, that really depends on sort of knowing about the adjunction properties of these functors. And you don't have that anymore. But Bezrukhovnikov supplied a different argument to construct this. So I'm going to write IC with script letters for the coherent version of IC. So for the IC functor, you can use a clever argument of Bezrukhovnikov, which substitutes adjunction properties there with sort of a heavier reliance on the duality functor. So this relies a lot more on knowing that the duality functor is there and does what you think it does. And so that means that problem 3 is still going to be a big problem. But let's suppose we just ignore that for now. So now if we take the first fix, that's the fix to problem 1 by working with equivariant sheaves, plus the second fix, which is the argument due to Bezrukhovnikov that lets us construct the category and the IC functor without using these functors, and just ignore the third problem by assuming that all orbits have even dimension. And all orbits with odd dimension would also be okay. You can make it even a little bit more general than that if you're careful. But roughly you need something like this. And then you get you get the theory of perverse coherent sheaves. And then Bezrukhovnikov has studied perverse coherent sheaves on the nilpotent cone for a complex reductive Lie group, where, well, of course, the nilpotent orbits all have even dimension. So this condition is okay. And then you get applications to various things. The two that I know something about are an old conjecture of Lustig and Vogin, and then a different conjecture of Humphreys on tilting modules for a quantum group. Okay, so I haven't mentioned the word staggered sheaves yet. So let me do that now. So the original motivation for staggered sheaves was to provide some sort of genuine fix for the third problem, and just to see what came out of it. And here's the fix for it. We're already constrained to working in the equivariant setting in order to make sure that a notion like constructible is well behaved. So now that we have this group action, the idea is to use that group action to get some extra information about the structure of the objects that are sitting around. So here's the kind of thing we're going to do. So on each orbit, find a suitable copy of the multiplicative group inside the isotropy group. And it's going to satisfy some axioms which I won't write down carefully. And this collection of data, this choice of a GM for each orbit, this collection of data altogether is called an S structure. And here's how this S structure comes into use. So on a single orbit, I'm going to write down some things for an analogy. A perverse sheaf is just a shift of a local system. So there's some local system, and there's a shift which depends on the stratum, so I call it D sub S, and that's it. A perverse coherent sheaf is exactly the same kind of thing. It's now a vector bundle, and it also has some shift that depends on the stratum. And then in the new definition, a staggered sheaf is going to be, well, it's going to be a vector bundle again, because we're still in the coherent setting. And then there's going to be some shift that depends on the stratum, and then some additional shift that depends on the weight of the chosen GM on that orbit. So that GM is contained in the isotropy group, so it acts on some fiber of the vector bundle, and the weight of the GM action on a fiber. Okay. So So now here's the first theorem about these things. So this was proved by me in the first paper in the list of papers that used to be up there. But then in joint work with David Truman, we found a better proof, which is also more general. I guess I've been leaving out various assumptions and, well, various sort of technical axioms throughout, but so I'll keep doing that. So with suitable assumptions, there exists a D stable, so here D is Serre-Grothendieck stable, of course, a D stable abelian subcategory, which from now on will be denoted M of X. So M of X is the category of staggered sheaves, and it's inside the bounded derived category of G equivariant coherent sheaves. With the property that that the restriction to an orbit of this construction is of the form that I specified at the bottom of that chalkboard. Okay. And then, moreover, so there are two properties that one gets right away, which are the same two properties that I mentioned at the beginning of my talk for perverse sheaves. One is that every object has finite length. And two is that there's a way to construct all the simple objects. Simple objects are given by a suitable kind of IC functor. So let me spell out what's going on with the simple objects a little bit more.
A question, so that you write not there exists the unique, but just there exists? Is this what?
Oh, the non-uniqueness here has to do with the choice of a perversity function, which plays the same kind of role as it does in perverse sheaves. Yeah, so that I guess there's a little bit more data to go in because you have to pick that data which I called an S structure. So I guess if you regard that as fixed and the perversity function is fixed, then this is unique.
It induces automatically the case of the need cone, right?
Sorry?
It induces automatically the case of the need cone, right?
I'll talk more about the nilpotent cone at the end. So Bezrukhovnikov has studied perverse coherent sheaves on the nilpotent cone quite a lot, but there isn't an obvious S structure there, and I haven't exactly understood how to make the connection between these two things. So.
Kind of confused. You say you need a choice of a perversity, but in the
That's true.
case you don't.
That's true. You don't need a choice of a perversity. Right. So for ordinary perverse sheaves, there's sort of only one perversity which has all the good properties that one wants. Okay. So. Okay, so let me sort of amplify this statement about simple objects. You can consider the set of isomorphism classes of simple staggered sheaves. And they're labeled by pairs S comma L, where S is an orbit and L is an irreducible equivariant vector bundle. And then a particular pair. I'm sort of writing down nothing here except notation. A particular pair SL corresponds to the simple object called ICSL. So so there's no content there except saying that the IC functor produces simple objects. But there's a little bit more we know about that already just from the setup of this category here. We know that IC, well, I guess there are a couple of things we know. One is that as with usual perverse sheaves, ICSL is supported on the closure of the stratum you started with, so it's or the orbit you started with, and its restriction to the open orbit in its support, which is S itself, is something specified. For ordinary perverse sheaves, I would just write L with an appropriate shift as I wrote it there. So here I have to write down ds plus the weight of the GM action. Okay. The stuff that's that seems to be, at least to me, the most remarkable is that this category has a lot of surprising properties. Like I said at the beginning, the goal was just to find a more general way to fix problem 3 in the original setup. But once you fix it in this way, if you pay attention to this number in these brackets, it turns out that the category has a lot more structure. So I want to call this number in brackets. I'm going to call this let's call this the weight of ICSL. And here I mean weight in the sense of eigenvalues of, by analogy with eigenvalues of Frobenius, not weight meaning character of a torus. So from that you can perhaps predict the next theorem. So here are some more theorems about staggered sheaves. So with that definition, we have a map which I'll call WT for weight from simple staggered sheaves to the integers, and then the theorem, which is also joint work with David Truman, is that with this weight function, M of x is a mixed category. And I'll explain more about that in a moment. Of course, the sort of archetypal example of a mixed category is that of perverse sheaves. So L-adic perverse sheaves. I guess you actually have to be a little bit careful here. Maybe L-adic perverse sheaves with semi-simple action of Frobenius. But certainly that's where the motivation for this notion comes from. And what this statement is it's an X vanishing statement. It says that if you take two simple objects, so let's say I see S prime L prime and I see SL. So if the weight of ICS prime L prime is at least as big as that of ICSL, then there's the X1 group between those objects vanishes. So maybe I should have written them in the other order. So yeah, so if you take X1 with the non-prime one first. Then that vanishes. I guess this is not quite the language in which we phrased it in our paper. Instead, what we wrote down was some more along the lines of using this kind of knowledge about GM actions on individual orbits to write down some sort of filtration of the whole derived category, and then the theorem said that a simple object in the category of staggered sheaves is pure with respect to these filtrations.
Is this staggered sheaves now somehow the heart of a T-structure?
Yeah, it's the heart of a T-structure. Yeah. And here are a couple of quick consequences of being a mixed category. One is that you get a similar extend vanishing statement. That may not be so exciting in and of itself, but the second thing you get is that every object, so every staggered sheaf, has a canonical filtration which comes about by looking at the weights of the simple subquotients, and this is called the weight filtration. So the simple subquotients of minimal weight are actually subobjects. The simple subquotients of maximal weight are in fact quotients, and so on. So that's the weight filtration, so there's a canonical filtration, and the subquotients of that filtration are pure, meaning that only one weight occurs. And the third thing is that pure objects are always semi-simple. So maybe I'll just write that in. So pure means only one weight occurs. Okay. So there are a couple more results I want to mention. And these all, well, some of them are about the structure of the category in general, but they come about from considering an open inclusion. So let's say J is the inclusion of a G-stable open subvariety. Okay, so some open union of orbits. Well, one of the problems at the beginning of the whole setup is that pullback doesn't have adjoint functors in the derived category of coherent sheaves. So J upper star, well, this is an open, so J upper star and J upper shriek are the same. So this has no adjoints that go from, well, where you would want an adjoint to go would be from the bounded derived category of coherent sheaves on U to the same thing on X. But something strange happens, which is that if you just stick to the abelian category of staggered sheaves, then this functor has adjoints on both sides. Just for convenience or familiarity or something, I'm going to call them J lower star and J lower shriek. But these are not the usual push forward or extension by zero of sheaves. I mean, in particular, the object you get by the adjoint functor, which I'm going to call J lower shriek, certainly does have non-zero stalks on the boundary. And these are functors that go from staggered sheaves on U to staggered sheaves on X. And then you can use these functors to construct new examples of staggered sheaves. In fact, so you can use these to construct standard and co-standard objects in the category of staggered sheaves. So corollary of the existence of these adjoints is that the category of staggered sheaves has the structure of a quasi-hereditary category. I'm being a little bit sloppy here because I think sometimes the word quasi-hereditary means, in particular, that there are finitely many simple objects, which is certainly not true for staggered sheaves in general. And sometimes it also includes an X-vanishing assumption between standards and co-standards, which is also not true here. So I'm going to state two more theorems, one of them, well, I guess I'll mention it when I get there. So one thing you can do after you have this information is that you can study the weight filtration, which is this canonical filtration coming from the mixed structure of the standard and co-standard objects. And then you get a new theorem on X vanishing, and here's what the theorem says. Well, we already had one constraint on X1 groups, which is just part of the statement that the category is mixed. The stronger statement is the following. X1 of ICSL to ICS prime L prime can fail to be, well, it can be non-zero only if the weights of those two simple objects differ by exactly 1. So weight ICSL equals the weight of ICS prime L prime. Well, we already knew that this had to be strictly strictly bigger. So this has to be the case. This is related to the property of being a Koszul category. Well, certainly this is a property that holds in Koszul categories. And then the last statement is that the category of staggered sheaves has enough projectives and injectives. For some definitions of quasi-hereditary, this is automatic, but this is not automatic here. I mean, it doesn't follow from the definition because the X vanishing between standards and co-standards need not hold. So this takes a little bit more work. Okay, so I guess in the last few minutes I'll say a little bit about the examples that are known. So I guess what I want to say about this is that well, all these last two theorems they were surprises to me. I wasn't expecting such things to be true at the beginning, so maybe one has to worry about whether I mean, these statements might turn out to be empty, for example, because before even setting up the category, you need to choose things like an S structure. So you have to ask whether on varieties that you know and love, whether you can make such choices in a way that gives you something interesting. So here are the examples that I know something about. And I guess I know enough about these examples to know that this theory is not empty. But I don't know a lot about even the examples I'm going to mention. So the first is on flag varieties. So flag varieties with the action of the Borel. So stratified by orbits of the Borel. And this was joint work with Dan Sage, and this was sort of quite early on in the story, and all we did here was calculations to produce a nice S structure. So, and by the way, it's true that you can cook up a variety where there is no S structure. So that is a danger. But flag varieties have one. Not more generally, in different generality. Toric varieties have been studied by David Truman, so I wasn't a co-author of that paper. But anyway, in this paper, he sort of classified the possible S structures in the kind of language that's appropriate to sort of toric variety combinatorics, maybe did a little bit in the way of computations of what these objects actually look like.
The G action, you need the action of G, right?
So here the group is the torus. Yeah. And the last example I want to mention is well, it's kind of embarrassingly small. It's the nilpotent cone for the symmetric space SL2C mod SO2C. So this is via the constant Sakaguchi correspondence. So this is something like the nilpotent cone for the real group SL2R. Here, the interesting thing that happens is that, well, you can look at the bijection between simple staggered sheaves. So there's a bijection between simple staggered sheaves and, well, this category has enough projectives, so take the indecomposable ones. And this appears to be related to a conjecture of Vogin, which is some general statement for nilpotent cones of real reductive groups. And in the special case of SL2R, this conjecture of Vogin becomes something like a bijection between pairs consisting of an orbit and a vector bundle and weights for SO2C. And here, weights means characters of that torus. I guess I could just write characters. So here are a couple of things which would be nice to understand. One would be just to compute more examples of these ICs. In this nilpotent cone example, I worked out what all the IC objects are, but even on flag varieties, the calculations we did don't tell you, what. I mean, the problem is sort of analogous to a standard problem with constructible perverse sheaves. What are the stalks on the boundary of the orbit you start with? So even on a flag variety, we don't know what those are. So on more varieties, I guess. And then maybe the last thing I want to mention is that so going back to perverse coherent sheaves, which are due to Dulin and Bezirkovnikov. So perverse coherent sheaves, remember, have this assumption that the orbits are even dimensional, and they don't involve things like the choice of an S structure. You can sort of think of them as a sort of degenerate case of staggered sheaves, where you take the trivial S structure. But in general, the theorems I've talked about in the last part of the talk really require a non-trivial S structure. So in general, it's not true that perverse coherent sheaves form a mixed category. So they're not mixed or quasi-hereditary. But on the most important example, they are. So on the nilpotent cone, they're mixed and quasi-hereditary but in rather a different way from staggered sheaves, in a non-local way. And what I mean is that the mixed structure on the whole category and the quasi-hereditary structure don't give rise to analogous structures for perverse coherent sheaves on a locally closed subvariety. So this is somehow some global feature of the category. Well, I guess I don't understand enough here to formulate a precise question, but the question should be something like, how are these features of this category related to something in the language of staggered sheaves that comes out of the other results that I've talked about? So, okay, so I'll stop there.
Thanks so much. Any questions or comments?
Does it work if the ground field is of positive characteristic?
It works if the ground field is a positive characteristic. Sometimes there's a little bit of stuff to pay attention to in these axioms for an S structure, which I didn't write up. But for example, flag varieties and positive characteristic are certainly okay.